good day to all of you. We are UTEM students from Faculty of Electronic and Computer Engineering, Semester 1, Year 2, and from BEng Section 2. We are now doing Engineering Mat 2 assignment, and our course code is BEKG 2443. Our lecturer's name is Dr. Noarzlina binti Abdul Razak for this subject. And okay, now let me introduce myself. My name is Nick Zari Adam bin Adli Nazrin, and my teammate is Muhammad Aizat Zaim bin Zaini, then Muhammad Fauzan bin Abdul Hakim, and lastly Ahmad Muzamin bin Rosliza. Okay, let's proceed to the introduction. This topic is about vector field. As we know, vector field is an assignment of vector to each point in a subset of space. Okay, let's see. For instance, a vector field in the plane can be visualized as collection of arrows with a given magnitude and direction, and also each attached to a point in the plane. Also, we need to know that vector fields are often used to model, like for example, the speed and direction of moving fluid throughout space, or like the strength and direction of some force, such as the magnetic or gravitational force, as it changes from one point to another point. Okay, that's for vector field. Now let's proceed to the next part. Okay, now it's a vector calculus. What is vector calculus? What can be related with the vector field? So, vector calculus is also known as vector analysis, and it deals with the differentiation and integration of vector field. And it also can be represented as distribution of vector to each point in the subset of space. It has two operations whereby it can be performed under vector field, and also play a basic role in the application of vector calculus to fluid flow, electricity, and magnetism. Each operation resembles differentiation. However, one produces vector field and the other one produces scalar field. So, vector analysis is an analysis which deals with the quantities that have both magnitude and direction. Also, to know that vector calculus deals with two integrals that called line integrals and surface integrals. So to understand more about this topic, the next part will be explained by my teammate in detail.
Okay, Bismillahirrahmanirrahim. Before that, I want to thank you for to Nik Zarid for explaining explain about the vector field and the vector calculus. So for my part, I will explain about the application of the vector. As you can see on the left side is a figure of the vector. So the red point is a charge denoted as Q, and the line and with the arrow is a vector field. So this is an electrical field for this part. So the first one is an electrical field denoted as E, is set up in the region of the space or around the charge. So the second point is to integrate the potential electric field. So I head into the next slide. So as you can see on the left side is a figure of how the charge is moving. So the blue line is the path, and this one is point A, and this one is point B. Okay, the first point is consider the work done in moving charge between 2 points A and B. So the second point is the electrostatic potential difference between 2 points A and B as the work done in the moving unit charge Q is equal to 1 between those points. So the equation for this formula is, we're using this formula, integral A to B E dl. So for this solution, we're using a partial differential to solve our problem. So this is an example of partial differential. So we're heading to the next slide. Okay, on the left side is a graph, potential versus the distance. Okay, the first point is the electric field is the vector gradient of the potential. Is electric is equal to negative V. So the second point is the electric field lines point from height to the low potential. As you can see, this part is a height and this one is a low. So height to the low potential. So the third point is the magnitude of the rate of increase in the direction. And last but not least, similarly, the rate decrease is greatest in the direction of minus v. So that's all for my part. I will pass to the next presenter to explain about more detail about our question. Thank you.
Okay, for the question 1, we are doing electrostatic potential. And here is the question. Engineers working on the design of equipment such as cathode ray tubes and electrical valve, which are commonly known by the generic term vacuum tube, need to calculate the electrostatic potential that results from an accumulation of static charges at the various points in a region of space. Complicated example require the use of a computer. Now let us consider a simple example. The electrostatic potential V in a region given by V equals to y over x squared plus y squared plus z squared to the power of 3 over 2. Suppose a unit charge is located in the region at the point with coordinate 5, 2, 0 and 0. Find the direction at this point in which the rate of decrease in potential is greatest. Okay, here is the equation. First, we simplify it from y over, we simplify it to y times with x squared plus y squared plus z squared to the power of negative 3 over 2. Now to find the delta v, which is partial derivative, delta v over delta x. So we just differentiate the x. Since x only exists in the second function, so we only differentiate the second function. Okay, then we will get y times with negative 3 over 2 times with x squared plus y squared plus z squared to the power of negative 5 over 2, and times with to the function in the inside, and we get 2x. The result, the final equation, we get negative 3xy times with x squared plus y squared plus z squared to the power of negative 5 over 2. And then the second, we derive it to the y. So delta v and delta y. Since there are two function of y, so we must use product rule, where we assume u equals to y and v equals to x squared plus y squared plus z squared to the power of negative 3 over 2. And then we find the derivative of du and dv. And lastly, we just insert the value inside the product rule. We will get the final equation, negative 3y squared times with x squared plus y squared plus z squared to the power of negative 5 over 2 plus with x squared plus y squared plus z squared to the power of negative 3 over 2. And lastly, we derive it to the z. Delta v over delta z equals is the same step as the x, since there are only one function of z. So we use the similar step, y times with negative 3 over 2 times with y squared plus y squared plus with z squared to the power negative 5 over 2 times with 2z. We get it from the differentiate z squared. Then the final equation, we will get negative 3 yz to the times with x squared plus y squared plus z squared to the power of negative 5 over 2. And lastly, since we know the coordinate, which is 5, 2 and 0, x is 5, y is 2, z is 0. So we just insert it inside the delta v over delta x and delta v over delta y, delta v over delta z. So we just insert the value. For delta v over delta x, the final value we will get negative 0.0066. Okay, and for delta v over delta y, the final value we will get 0.0038. And for delta v over delta z, because z is 0, so the whole equation will become 0. And lastly, we will input into the delta V equals to delta V over delta X I plus with delta V over delta Y J plus with delta V over delta Z K. And since we already get the value, so for delta V, which is the rate of increase, we will get negative 0.0066 I plus 0.0038 J. For the rate of decrease, we just inverse the inverse the sign to negative delta V. We will get the negative will become positive 0.0066 I minus. Okay, this is my mistake. Okay, I have fixed the mistake I have made. So the final rate of decrease will be 0.0066 I minus with 0.0038 J. Okay, that is all from me. Thank you.
Okay, thank you, Muzammil. Now I will explain another application of vector calculus in electrical field. So, for example, we have a problem here. It says that the volume charge density P is the divergence of electrical flux density D. Suppose the electric flux density is equal to D with an equation of Y times X times exponent of X with component of AX plus AX squared times Y with component of AY. So it says that we need to find the volume charge density of D. We know that the volume charge density is actually the divergence of the electric flux density. So as you can see here, the formula for the charge density is equals to the divergence of flux. So we know that the component of AX is equals to Y equals to X, and this one is equals to X squared Y. So we component into our partial differential for dAX and dAY. Since dz is not here, we will consider it as 0. So we just put all the components into the partial differential, and we know that we need to differentiate for Y, X, and exponent of X, and X squared Y with respect to X and Y. So from the first partial differential, we have to use product rule. So the product rule can be calculated through this. So we assume U equals to X and U prime will be 1, and exponent X will become exponent S if we differentiate it. So the product rule is U prime V plus V prime U. So we will have 1 EX plus X EX. So if we insert back our total of partial differential, we will get Y exponent X times X plus 1. So for the second term, we will have a straightforward answer, which is the X squared. So the final answer will be the divergence of the charge density, which is equal to the divergence of density flux, will be Y times exponent X times X plus 1 plus X squared. So in conclusion, we can say that we have demonstrated the application of vector calculus in terms of engineering application in electrical field. This example is shown by using gradient of vector and the divergence of vector. That's all from us. Thank you.